This video is about coordinates. We have three objectives. We're going to define a coordinate mapping. We're going to do some examples where we find coordinate vectors. And then we're going to use the isomorphism from V to Cn to answer some questions about sets in V. We'll start by revisiting the unique representation theorem that we saw in a previous video. This theorem says that if I have a basis, B, for some vector space V, then any vector x in V can be written uniquely as a linear combination of the basis vectors. And in particular, these scalars, C1 through Cn, that multiply the basis vectors here are unique. The proof is essentially the same as we saw before, so we'll skip that for now. Now we're going to define coordinate vectors using that unique representation. In other words, if B is a basis for a vector space V, and x is some arbitrary vector in V, well, we know that x can be written as a linear combination of those basis vectors by the unique representation theorem. And furthermore, these c's are all unique. So we're going to define the coordinate vector of x using this notation, the Greek letter rho with a subscript b of x, and this will be read the coordinate vector of x relative to the basis b, and it will simply be equal to a vector in Cn whose entries are the n coefficients c in the unique representation of x. As we'll see later, this actually defines an invertible linear transformation, in other words, an isomorphism. So we'll define a mapping called rho sub b from V to Cn such that rho of x is equal to this coordinate vector, and it'll turn out that that's an invertible linear transformation, and it will be very useful. First, though, let's do some examples. So we're going to look at some examples of coordinates or coordinate vectors in Cn. So let's say I've got this basis here, b for C2, and this vector x in C2, and I want to find the coordinate vector of x relative to this basis. Well, I use the defining equation. X can be written as a linear combination of the basis vectors. In this case, we call this one b1 and this one b2. We can write x as a linear combination like this, with some coefficients C1 and C2 that we need to solve for. Remember, these coefficients will be the entries in the coordinate vector. So I've got this vector equation. I'll replace b1 and b2 with the vectors from the basis, and I'll replace x with the given vector. And now I can see I've got a vector equation. I can write the corresponding matrix equation, rho reduce the augmented matrix, and I can see that I've got a unique solution here. So here's our solution, and that means the coordinate vector is the vector 3, 1. In the next example, we have this vector x in C3, and we're asked to find the coordinate vector of x relative to E, where E is the standard basis for C3. So here's E1, E2, E3, and the basis E is the set containing E1, E2, and E3. Now I'll use the definition of the coordinate vector, and I'll write x as a linear combination of the basis vectors E1, E2, and E3. I'll replace E1, E2, and E3 with the vectors from the standard basis, and I'll replace x with the given vector. Now normally to solve this vector equation, we would do what we did in the previous example. We'd write a corresponding matrix equation and solve that matrix equation by rho reducing the coefficient matrix. But this vector equation is so simple we can solve it by observation. So we can just observe the solution, and here is the coordinate vector. This is an important example, and we can generalize it like this. If E is the standard basis for Cn, the coordinate vector of any vector x in Cn relative to the basis E is simply that vector x itself. We say that we can just observe coordinate vectors relative to the standard basis, and this is in fact one of the reasons why it's called the standard basis. Now we'll do some examples in Pn. We'll find coordinate vectors in Pn. In this example, B is the basis x squared x and 1, and this is the standard basis for P2. We have this vector P, which is a second degree polynomial, and we want to find the coordinate vector of P relative to B. Well, we need to solve this equation where I've called x squared b1, x b2, and 1 b3. And this one is almost as easy as the previous example we did. This vector P is already a linear combination of these basis vectors. In other words, if I write P as a linear combination of the basis vectors, b1 is x squared, b2 is x, and b3 is 1, well, I can just observe the c's, because here's P. P is 3x squared minus 6x minus 2, which is given to us, and I need to figure out what C1, C2, and C3 are. Well, I can just observe. C1 has to be 3, C2 has to be minus 6, and C3 has to be minus 2. So here's the coordinate vector of P relative to B. Again, the reason that this set B is the standard basis for P2 is because I can just observe coordinate vectors for any vector in P2. The entries in the coordinate vector are simply the coefficients on the polynomial. But what if we have a non-standard basis for P2? For example, here's a basis D with these three polynomials, 2x squared minus x, x plus 1, and 5. And I've got the same polynomial P, 3x squared minus 6x minus 2, and I want to find the coordinate vector of P relative to D. It's the same vector P, but a different basis. Well, how does that change things? Well, we're going to solve the same equation now, except instead of a linear combination of the B basis vectors, we want to write P as a linear combination of the D basis vectors, where I've called this vector D1, this one D2, and this one D3. Well, we start with our linear combination again. On the left-hand side, I've got P. On the right-hand side, I've got a linear combination of the basis vectors with the C's as the coefficients. And if I combine like terms and simplify the right side, I can write the right side as some number times x squared plus some other number times x plus a constant, and set like terms on both sides equal to each other. So 3x squared has to equal 2c1x squared, and minus 6x has to equal minus c1 plus c2 times x, etc. So I get this system of equations, which I can write in the standard form like this. Write the augmented matrix, reduce it, and I can see, because I get the 3 by 3 identity here, I get a unique solution here. C1 is 1.5, C2 is minus 4.5, and C3 is 0.5. So here's my coordinate vector for P relative to the basis D. Okay, now we're going to generalize some of these examples and talk about an isomorphism from V to Cn. As I mentioned before, we can think of the coordinate vector as a linear transformation. So if V is an n-dimensional vector space with a basis B, the transformation, rho sub B from V to Cn, is called the coordinate vector transformation for V relative to B. And here's the function rule. Rho sub B of x, the coordinate vector of x relative to B, is equal to the coordinate vector. Well, this is just an equation that defines the coordinate vector here, but now we're thinking of it as a linear transformation, and this is the function rule for the linear transformation. And of course, the C's come from writing x as a linear combination of the B basis vectors. Our first theorem here says that if B is a basis for the vector space V, then this coordinate vector transformation is an isomorphism. Now in the book, they split this into 4 different theorems. They show that this transformation is linear, injective, surjective, and invertible. In the notes here, I combined all of those things into one because they really all combine together to mean isomorphism. Remember that an isomorphism is an invertible linear transformation, and invertible means injective and surjective. Since there's a lot to show there, the proof is pretty long. We need to show that the transformation is linear, one-to-one, and onto. Remember, one-to-one is the same as injective, onto is the same as surjective. For the sake of time, I'll skip the details here, but it's worth going through this because this is slightly different than what's in the book because all 4 steps are combined together into one. Once we have that theorem, the next theorem is trivial to prove. Every n-dimensional vector space is isomorphic to Cn. Well, if V is an n-dimensional vector space with a basis B, here's an isomorphism. Remember, isomorphic means there exists an isomorphism from the vector space to Cn. If we call the vector space V, the isomorphism is the coordinate vector mapping that we just saw. So because an isomorphism exists, V is isomorphic to Cn. The next 2 theorems, 4.3 and 4.4, lead up to 4.5. And in fact, theorem 4.5 is just a combination of these 2. Theorem 4.3 says if V is an n-dimensional vector space with a basis B and S is some set of vectors in V, then S is linearly independent if and only if the coordinate vectors, the set of coordinate vectors R in Cn, is linearly independent. Similarly, if V is n-dimensional with a basis B, I've got the same set S here. The span of this set is equal to V. In other words, this set spans V if and only if this set spans Cn, or the span of the set containing the coordinate vectors is equal to Cn. We can summarize that like this. Linearly independent sets in V correspond to linearly independent sets in Cn. That's what theorem 4.3 says. Theorem 4.4 says spanning sets in V correspond to spanning sets in Cn. Well, a basis is a linearly independent spanning set. So not surprisingly, we have the next theorem then that says if V is an n-dimensional vector space with basis B, and again, if S is a subset of V, then S is a basis for V if and only if the set R of the corresponding coordinate vectors is a basis for Cn. We sometimes summarize the previous three theorems by saying isomorphisms preserve linear dependence relations. For example, if I've got vectors y1, y2 up to yp in V, and I write x as a linear combination of those vectors y. Now, these don't have to form a basis. These are just any arbitrary vectors in V, and x is a linear combination of those vectors. Then the coordinate vector of x relative to some basis b for V is equal to the same linear combination, meaning the c's here are the same as the c's here, of the coordinate vectors of these y's. Here is a specific example that illustrates that. Let's say I've got three vectors, x, y, and z, in some vector space V, and u is this linear combination, 3x minus 7y plus 4z. If there's a basis b for V, the coordinate vector of u relative to b is equal to 3 times the coordinate vector of x relative to b, minus 7 times the coordinate vector of y relative to b, plus 4 times the coordinate vector of z relative to b. And the 3, the minus 7, and the 4 are the same coefficients in both linear combinations, here and here. Earlier, we talked about the standard basis for Pn, and in this example, we derive it based on the characteristics we would like it to have. Remember, we saw that in Cn, where E is the standard basis for Cn, the coordinate vector of any vector x in Cn relative to the standard basis is just equal to x itself. Now, it's a common mistake to try to do this in Pn. If P is a vector in Pn, it is not the case that the coordinate vector of P relative to some basis d is just equal to P. Notice the form of this equation, coordinate vector of x relative to E is equal to x. But in Pn, that doesn't work. There is no basis for Pn such that the coordinate vector of some vector P in Pn relative to that basis is just equal to P itself. This is because this coordinate vector is in Cn. It's not in Pn. P is in Pn, which is a totally different vector space. P is a polynomial. The coordinate vector is a column vector. But we can find a basis that's almost as nice in the sense that we can observe the entries of the coordinate vector without doing any extra work. So let's see if we could construct a basis d, d0, d1 up to dn, for Pn, so that if I have some arbitrary polynomial, which is also a vector in Pn, then the coordinate vector is simply the coefficients. So I can just observe by looking at the polynomial what the coordinate vector is. These would be the coefficients of the basis vectors d in the linear combination for P. So P is equal to a0, d0, plus a1, d1, etc., up to an dn. And P is this polynomial, a0 plus a1x plus up to an x to the n. Well, clearly, this equation is satisfied if we simply let d0 equal 1, d1 equal x, d2 equal x squared, up to dn equals x to the n. So here's our basis, 1x, x squared, up to x to the n. And this is called the standard basis for Pn because we can just observe the coordinate vectors relative to this basis without doing any calculations. Okay, now we're going to do an example that shows the real power of the isomorphism from V to Cn. Here is a set B of polynomials in P2, and I want to show that this set is a basis for P2. Normally, I would need to show that this set B is linearly independent and that it spans P2, and that would involve quite a bit of work for each step to show that it's linearly independent, and then separately to show that it spans P2. Now, since there are three vectors here, 1 plus x squared, x plus x squared, and 1 plus 2x plus x squared, and I know that P2 is three-dimensional, I can skip one of these steps. I could show that it's linearly independent, and since there are three vectors, I know it's a basis, or I could show that it spans P2, and since there are three vectors, I know it's a basis. But we're going to do something even easier. We're going to use an isomorphism. At first, it may not be obvious why we're doing what we're doing, but it should become clear at the end. So what I'm going to do is I'm going to let D be the standard basis for P2, the one that we just talked about in the previous example, 1x, x squared. I already know this is a basis for P2. This is the standard basis for P2. Then I'm going to take each of the vectors in the set B and label them. I'll call the first one B1, the next one B2, and the last one B3. So B is now this set. And I can write B1 as a linear combination of the basis vectors D. Remember, D1 is 1, D2 is x, D3 is x squared, and I'm going to write each of these B basis vectors as a linear combination of the D's. So 1 plus x squared I can write as 1 times 1, which is 1 times d1, plus 0 times x, which is 0 times d2, plus 1 times x squared, which is 1 times d3. Similarly, for b2 and b3, I can write them as linear combinations of these d basis vectors. And by observation, I can write down the coordinate vectors. So the coordinate vector of 1 plus x squared relative to this basis d here is 1, 0, 1. I just read the entries in the coordinate vector off of the linear combination. The coordinate vector for b2 is 0, 1, 1. The coordinate vector for b3 is 1, 2, 1. Okay, so what good is this? Well, by the theorem that we just saw, if this set of coordinate vectors is a basis for C3, then this set containing the b's is a basis for P2, which is what we're trying to show. Well, it's a lot easier to work with this set of column vectors. How do we show that a set of column vectors is a basis? Well, we just put them into a matrix and row reduce it. So we'll construct this matrix A, whose columns will be the coordinate vectors. Here it is. We row reduce it, and we get the 3 by 3 identity. So by the invertible matrix theorem, we know that the columns of A form a basis for C3, and by the isomorphism, the set B is a basis for P2. Okay, that finishes our video on coordinates. We defined the coordinate mapping, we did some examples about how to find coordinate vectors, and then we used the isomorphism from V to Cn to answer questions about sets in V, in particular whether a given set was a basis for V.